On time. We're going to give the stragglers another minute to come in and remember how to register and everything, and then we'll get started. Okay, I'm showing 1 minute past the hour, so we're going to go ahead and get started on our seminar. Welcome, everybody, to our LPI seminar this week. We're really excited to be joined this week by Dr. Michelle Thompson, who some of you may remember here from her time as an NPP with ARES. So we're happy to welcome you back, Michelle. And since then, Michelle has moved on and is an assistant professor at Purdue University since 2018. And she's come back with us this week to share some of her work. And the title of her talk is From Atomic Scales to Asteroid Surfaces, Understanding Space Weathering of Asteroids Through Analysis of Samples Returned by the Hayabusa 2 mission. So our format, as usual, it's going to be that we're going to save questions until the end. So if you do have some burning questions, you can write those in the chat box and I'll read them off to our speaker at the end, or you can just wait and virtually raise your hand at the end and I'll call on you to unmute yourself and ask your question. So with nothing else for me to say, I will turn things over to you, Michelle. Thanks so much for being here.
Perfect. Thanks so much, Sam. Really excited to be here. And I want to talk today about some of the work my group's been doing over the last few years to try and understand the evolution of airless surfaces across the solar system more broadly, but specifically carbonaceous asteroids. But before I do that, I just wanted to point out that before I was an NPP, the last time I gave a talk to LPI was in 2009 at the end of my intern class that year. I was an intern in 2009 and I did some work with Roy Christofferson over at NASA JSC. And that was a really instrumental and formative experience for me and kind of set me on the pathway to having a career in planetary science. So I just wanted to acknowledge the importance that LPI had in my career trajectory. And one thing that I definitely came out of the LPI internship knowing I wanted to do was studying planetary materials. So I thought I'd start out with a little bit of context about the kinds of questions that I ask. So when I think about studying planetary materials at the highest level, I separate the types of questions that you can ask into two different themes. The first is questions of origins. So what processes were going on to form different planetary bodies? What led to the diversity of different solar system bodies operating really in the early solar system? And the second question or theme is about evolution. So after their initial formation, how have planetary bodies been modified? That includes processes that are going on, in the early solar system and throughout solar system history, but also active processes that are working to modify these solar system materials through time. So my work mostly focuses on the second theme, which is these questions of evolution. And I focus pretty exclusively on airless bodies. So that includes the moon, asteroids like Itokawa, Bennu, Ryugu, but can also be expanded to planets like Mercury or main belt asteroids. And because these airless surfaces don't have atmospheres that can protect them from the harsh interplanetary space environment, they're being modified in really specific ways. So I study the surface processes that are going on airless bodies through a lens of return sample analysis, but also through experimental techniques simulating these processes in the laboratory. And I'm going to actually talk about both of those today. So I work most broadly on questions of solar system evolution, but I'm really interested in one process in particular, and that is a process known as space weathering. Space weathering is a phenomenon that's occurring across the solar system on airless surfaces that alters the material on the regolith on those airless surfaces because of its exposure to interplanetary space. It's really driven by two primary processes. The first is micrometeorite impacts. These are hypervelocity dust particles that are hitting the surface, that are melting material in the regolith. They're vaporizing material, and that melt and vapor that's recondensing in the surface regolith. The second process is the interaction of surface material with energetic ions from the solar wind. It's predominantly hydrogen and helium, although we can have some heavier ions as well. And those ions are being implanted into the surfaces of these grains in the regolith. They are amorphizing the crystal structure, meaning they're breaking down bonds in the mineral, and you're losing that crystal structure. They're sputtering particular ions and elements from the surfaces of these grains. They are redepositing those sputtered ions, and they're developing these vesiculated or bubble textures on the surface as well. And both of these processes are working together to change the morphology of the grains on the surface, the microstructure, and the chemical composition that we observe in a sample set. They're also working together to modify the spectral characteristics or the optical properties of these regolith grains. And the spectral characteristics is one of the first ways that we recognize that space weathering was a process occurring on the surfaces of these bodies. So when we got samples back from Apollo and we started looking at them in the laboratory, we were interested in studying them, scientists were interested in studying them with spectroscopic techniques, in particular reflectance spectroscopy. So you're looking at how light is reflected off the surface of these regolith grains, and the characteristics of that reflected light can tell you about the minerals that you have in the sample, about the composition of those minerals, about the atomic configuration, all kinds of information. And this data is obviously really important for remote sensing spacecraft that we send to planetary bodies across the solar system. So when they started looking at the Apollo samples, they noticed something really interesting, that when they compared the reflectance spectra, so here's a plot of just reflectance versus wavelength, for a ground up lunar rock, meaning they had taken a rock that was collected on the surface of the moon, pulverized it, and made an artificial soil out of it. When they collected a spectrum from that material and compared it to a natural lunar soil, meaning a soil that was just scooped up on the surface of the moon and brought back, these two different types of materials had very different spectral properties. And there were three primary changes in the characteristics that we see in the soil versus the ground up lunar rock. The first one is that the soil samples are significantly darker, meaning they have a lower reflectance, lower albedo than we see for this ground up lunar rock. There's also an attenuation of characteristic absorption bands. These bands here are characteristic of different minerals in the sample, in this case of iron-bearing silicates like olivine and pyroxene from the lunar samples. In the lunar soil, we don't see any evidence of those characteristic absorption features. And then the third property that they recognized is that there was an overall reddening, or an increase in reflectance with increasing wavelength for the soil compared to the ground up lunar rock. So we knew that there was some process, in this case space weathering, that was operating on the surface of the moon, affecting these lunar soils, which was not affecting the interiors of these lunar rocks, which had not been exposed to interplanetary space. And we saw this characteristic if you corrected for the same grain size, for the same bulk composition, all of those things being held constant, you still see this optical change in our space weathered lunar soils. So then scientists started going to hunt around for what the microstructural and chemical evidence for this space weathering processes are. And they discovered characteristics related to space weathering down to the smallest scales. And I'm going to talk through, there's a lot of different image types, and you'll see some of these throughout the talk. So I want to give you kind of an introduction to what the image is and what kind of information you can get from them. So the first, this is just an optical image taken with a stereo microscope. The first type of particle they noticed was something called an agglutinate. Agglutinates are produced during these micrometeorite impacts on the surface of the moon. They're mineral fragments that are welded together by impact glass. And you can see some of the nice dark, shiny impact glass on the surface of this agglutinate. And these are one of the key characteristics that we see evidence for space weathering on the lunar surface. There's also evidence for solar wind irradiation. Now we're looking in the second image here at a scanning electron microscope, secondary electron image. So you're looking at the surface topography and morphology of the sample. There's a scale bar there. If you look closely, there are all these little this sort of hummocky texture or bubbles or blisters that are spread out across the surface. These are the product of implanted solar wind, hydrogen, and helium that's accumulated into these bubble textures. We can see more evidence for that if we were to take a cross-section of this grain and analyze it in the transmission electron microscope. So this is now a TEM image, this third image. Now you're looking at a cross-section. So this area here is the surface of the sample. You're going into the sample interior, moving down in the image. And this upper 100 to 200 nanometers of material is highly vesiculated. Each of these low or these bright areas are vesicles or bubbles formed from this implanted hydrogen and helium. So we see evidence for solar wind irradiation and micrometeoroids. There's further evidence for solar wind when we start looking at the crystal structure of the sample. So again, a TEM image where the surface of the grain is here, and you're going into the grain interior in this direction. And this is a high resolution TEM image, meaning if you notice the scale bar, we're able to see the atomic structure of the sample. So these fine scale parallel lines that you see up here, these are atomic planes within the crystalline material. In this area of the sample, bounded by this dashed line, you don't see that nice repetitive pattern of those lines. That's because this material has become amorphous, or the crystal structure is completely broken down because those ions are breaking crystal bonds in the sample. We see evidence for higher energy particles coming off the sun, in this case from solar flares. And those have a much higher energy. So instead of just being implanted up to, a few tens of nanometers into the surface, now they form these microstructural tracks or bullet holes that are transgressing through the entire thickness of the sample. And you can actually count the density of those tracks to figure out how long a grain might have sat on the surface of a planetary body like the moon. We also see the development of chemically heterogeneous surface layers. So again, the grain surface here, we see enrichments in elements that might be different from the underlying substrate. And then perhaps the most important characteristic that we see as a result of space weathering is the development of nanophase particles. These are predominantly iron metal on the surface of the moon. Here we've got two TEM images, and these are both what we call Z contrast images. So material that has a higher atomic number appears brighter. So each of these little bright spheres is a metallic iron nanoparticle that formed through space weathering on an airless surface. And these nanoparticles are what's really driving the changes in the optical characteristics that we see in our spectroscopic data. Okay, so we know that space weathering manifests at really small scales, but it has global impacts in terms of what we can observe with spectral data. But we can also just see it at the macro scale with samples in the lab. So this is the Apollo 17 core sample, which was recently released through the ANXA program. And this is representing the surface of the moon, and you're going into the interior and the regolith in this direction. You'll see all the grains at the surface are much, much darker, just optically to the naked eye, than they are compared to this underlying material. So we can recognize it from the nanoscale to the macro scale, all the way up to the spectroscopic global scale. Okay, so we know what it is, we know how we can recognize space weathering, but why is it important to study this process across the solar system? Well, after impacts, space weathering is probably the most predominant surface process that's going on across the solar system, impacting everything from Mercury to near-Earth asteroids to main belt asteroids, the moons of Mars, all the way out to the moons of the giant planets. And so to understand to improve our understanding of the evolution of these bodies, we have to be able to deconstruct how space weathering is changing their surface chemistry and grain mineralogy through time. Because this is a process that affects the spectral characteristics, we need to understand what's going on so that we can reliably and properly interpret remote sensing data from the surfaces of these airless bodies. You can imagine that if we're attenuating characteristic absorption features, it's going to be hard to determine what the true mineralogy of a surface is without understanding how space weathering is impacting it. We can also want to try and match meteorites that we have in our collections here on Earth to what their parent bodies are out in the asteroid belt. But asteroids are being space weathered, meteorites are generally not surface samples, and so it's difficult to be able to make those connections without an understanding of this process. And then finally, what I'm really interested in is being able to understand return samples to differentiate characteristics that we see in the samples that might be primary or as a result of their origin or their formation, and which characteristics form as a result of these evolutionary processes. And the overall goal for my group's work is to try and create a model for how space weathering operates across the solar system. This is not an easy feat because it relies on understanding a lot of different factors, what the impactor flux is for hypervelocity dust particles, what their velocity is, that varies with heliocentric distance in the solar system. So does the flux of solar wind ions that are coming off the sun. As you'll see throughout the talk, the starting composition or the mineralogy of the surface, it has an important effect on what types of space weathering characteristics we're going to develop. And then how often the surfaces of these planetary bodies are being resurfaced, either by large scale impact events that are refreshing larger regions on the surface, or things like gravitational interaction that's kind of shaking the surfaces of these planetary bodies. So we have to account for all of these different factors when we are trying to build a model for this across the solar system. Okay, so we know why it's important, but what kinds of techniques do we want to use to try and understand this process? Because it's affecting microstructure, chemistry, and spectral properties, we want to build a multifaceted approach to try and understand space weathering through really coordinated analytical techniques. That includes scanning electron microscopy and transmission electron microscopy to understand microstructure and composition. We also use X-ray computed tomography to try and look at what the internal structure of the grain is compared to the surface. If we're interested in organic functional group chemistry, we can use two-step laser desorption mass spectrometry to see changes in functional group chemistry. Then we can also simulate these processes in the laboratory using experimental techniques. For solar wind irradiation, we can do ion irradiation with hydrogen and helium. And for simulating the short duration, high temperature events associated with micrometeorite impacts, we can do pulse laser irradiation of materials in the lab as well. Then finally, we want to tie together all these observations for organic and inorganic chemistry and structure and perform laboratory spectroscopy to try and link that to our remote sensing data that we can get from spacecraft observations. Okay, so we know what tools we have. The primary tool that I'm going to be showing data from today is from the transmission electron microscope. Because space weathering really manifests down to the nanoscale and it affects microstructure and chemistry, we want to have a tool that can give us information for in both of those categories down to this small scale. So a TEM works much like a scanning electron microscope, if you are familiar with those, but you have a sample that you are accelerating an electron beam towards. In this case, the sample has to be very small and thinned down to electron transparency. That means less than 100 nanometers in thickness. And this is an example of one of the samples that we look at regularly in the TEM. The way that the electrons then interact with the sample can give you different types of information. You can get images, including images that give you structural information, like these atomic scale images here showing these fine scale parallel lines of the crystal structure. But you can also get quantitative chemical information using energy dispersive X-ray spectroscopy, and that tells you about the distribution of different elements in the sample and what space weathering might be doing to affect that. So I'm going to show these different data types today, but a lot of what we'll see is from the TEM. Okay, so now we have the tools, but what do we actually want to talk about? Well, our understanding is for space weathering is really built in the framework of the moon. We have return samples from the Apollo missions. We have a wealth of remote sensing data for the surface of the moon, but I wanted to ask the question, what happens for other types of airless surfaces, particularly carbonaceous asteroids? Carbonaceous asteroids are very complex in terms of their mineralogy and their composition, whereas the moon is predominantly made up of a few different silicate and oxide minerals. For carbonaceous asteroids, we expect that they are rich in organic molecules. They're very primitive. They've got hydrated phases like phyllosilicates, and they have diverse phases like carbonates and sulfates and sulfides and all different types of minerals that we're not used to seeing in the lunar sphere. Now, why are we interested in carbonaceous asteroids? Because there are missions that have or are currently returning samples from the surfaces of these. One of these is the Hayabusa 2 mission. You can see the collection of the sample from the Hayabusa 2 mission to asteroid Ryugu in this video. And then one of the coolest selfies that's probably ever been taken, which is the shadow of the spacecraft on the surface of the asteroid. And you can see the area that they sampled during the approach in this dark, disturbed material here. So we want to understand space weathering on carbonaceous asteroids so that we can get information about how space weathering is affecting these return samples. But in advance of those samples coming back, we can actually perform experiments to try and predict or help us better understand the characteristics in the return sample set. So what my group did was do some experiments to try and predict how these types of materials are going to weather. And we did 2 sets of experiments. The first was simulating solar wind irradiation using hydrogen and helium ions at the University of Virginia. And the second was simulating these short duration, high temperature impact events by using pulse laser radiation at Northern Arizona University. And for both of these experiments, we used the CM2 Murchison meteorite, which is a carbonaceous chondrite thought to possibly be analogous to material that we're going to be bringing, that we brought back from Ryugu and that will be returned by OSIRIS-REx. And we can expose the surfaces of these meteorite chips to ion irradiation. That work's being led by one of my graduate students, Dara Lasniak. And we can also perform these laser experiments on the surfaces of chips from the same stone. And you can see in these optical images just the area where the sample was subjected to laser radiation. The benefit of doing laboratory experiments is that you have control over timescales and exposure. So we know what the flux of our solar wind, simulated solar wind ions are. We can equate that to some sort of timescale on the surface of asteroid Ryugu. We can also do progressive laser irradiation to simulate multiple rounds of impacts or micrometeorite dust impacts on the surface as well. So we have these 2 different sample sets, and now I want to talk you through the data that we collected for our experimental results. First, we went to visible to near infrared spectroscopy to see what the changes in the optical characteristics were. We looked at changes in organic functional group chemistry using 2-step laser desorption mass spectrometry. And then we moved on to understanding structure and chemistry at the nanoscale using SEM and TEM. So I'll walk you through these data sets, the first one of which is our reflectance spectra. When we look at our absolute reflectance, in black, this is the spectrum from our raw unirradiated Murchison sample. Our laser irradiated sample, one that had experienced 1 round of laser radiation, is shown in purple, and 5 rounds of laser radiation is shown in green. Our hydrogen irradiated sample in red and our helium irradiated sample in blue. So both of these constituent space weathering processes. And what you may notice right away is that we've got conflicting trends about what's happening to the spectral properties in terms of their spectral slope and their overall reflectance between the laser irradiation and the ion irradiation. Our laser irradiated simulated micrometeorite samples are darker or have a lower reflectance compared to the unirradiated material. And across the middle wavelengths, they appear to be slightly bluer, meaning they have a decreasing reflectance with increasing wavelength. And that's the opposite of what we see in the lunar case, so keep that in mind. Our hydrogen irradiated sample looks pretty indistinguishable from our unirradiated material, but the helium sample shows some brightening, especially towards these middle to longer wavelengths, and some reddening across those wavelengths as well. So we are getting our first sense that micrometeorite impacts and solar wind irradiation might not be driving the evolution of this spectrum, at least from a slope perspective, in the same direction. We can then do a continuum removed observations to try and see what's happening to the absorption features. And overall, all of our characteristic absorption features are decreasing with either solar wind or micrometeorite impacts. But the one I want you to pay attention to is the 1.94 micron band, which is associated with water in some of our phyllosilicate hydrated phases. And so keep that in mind in the way that it is being reduced as a result of simulated space weathering throughout the talk. We can look at how organics analyses show us changes to the functional group chemistry as a result of simulated space weathering. So this is work that was done by Simon Clement at NASA Johnson Space Center. And there are two different ionization wavelengths for this system. One is sensitive to really all organic molecules, and the other is specifically focused on detecting aromatics. We can create these maps that show the concentration of organic molecules that are spread across regions of the surface that are unirradiated and regions that have experienced laser radiation. Warmer colors means there's more detection of those species. And so for both our ionization wavelengths, we see an increase in the organic molecules on the surface as a result of simulated micrometeorite impacts. We think that, we're melting material, we're vaporizing material. These organics are really volatile. They're probably preferentially being affected by this process, and then they might be recondensing or being redeposited onto the surface in this film that we're detecting with the micro L2MS instrument. We can do the same observations for our ion irradiated samples. And again, as is becoming a theme, we see an opposite trend from what we did for our micrometeorite impacts. Here we can create maps of the organic concentration across the surface, both in the hydrogen irradiated region, in the helium irradiated region, and then some areas that were not exposed to our simulated solar wind. Where the hydrogen irradiated surface really looks pretty similar in terms of the distribution of organics, our helium irradiated surface shows an overall reduction in the concentration of organic species. You can see sort of cooler colors here. It can be as high as up to 30 to 40% of reduction in the concentration of organics. We think this is probably due to a slow sputtering of these organic species from the surface. You've got hydrogen and helium ions in particular. They're heavy, they're coming in and they're knocking elements and ions off of these organic molecules. So again, we've got two opposing trends for what effects we're seeing from solar wind irradiation versus micrometeorite impacts. We can then turn to our SEM and TEM techniques to look at microstructure and chemistry. So this is a surface view. So it's just a plan view of the sample that had been exposed to simulated micrometeorite impacts. All across the surface, you see this melt deposit. It's very frothy. It's got a ton of vesicles or bubbles that appear to be burst from the surface. Then we can go in and take a cross section and look at the sample in the transmission electron microscope. So now you're looking at the surface of the sample here, and you're going into the grain, the sample interior in this direction. This is all the heterogeneous matrix of our carbonaceous chondrite, our Murchison sample. There are phyllosilicates in here, there are carbonate minerals, you have sulfide minerals. But what I want to draw your attention to is the surface. At the surface are these very characteristic melt textures. There are droplets that have this sort of spherical shape. There are also vesicles. These bright areas are bubbles that are spread not only throughout the melt layer that's across the surface, but are also concentrated at the boundary between the melt and this underlying matrix. And then we also see nanoparticles. Each of these dark spots is a nanoparticle. They're ranging in size up to 100, 150 nanometers in diameter. We can use our chemical techniques to try and understand what the composition of those nanoparticles are and determine whether they are iron metal like we see for the moon or something else. And these results show us that we have the nanoparticles are diverse in their composition, but as we increase the scale of the irradiation, they become dominated by iron nickel sulfides. You can see the hot spots in nickel and sulfur that correspond to these nanoparticles distributed throughout the melt. So this is a different composition from what we've observed in lunar samples that might be influencing the spectral characteristics in new ways compared to what we understand for the moon. When we compare the microstructure and chemistry of our laser irradiated samples, simulating micrometeorite impacts, to our solar wind samples, again, they could not look more different. For our ion irradiated material, now you're looking at the surface of the sample here, going into the interior here. We have this 100 to 150 nanometer thick, highly vesiculated region at the surface that's formed through the accumulation of this hydrogen and helium. And we see this across all different types of phases. Across the matrix, we see it in anhydrous silicate grains. We've got this consistent development of vesiculated material. What we don't see a lot of is the production of nanoparticles, whereas they're very abundant in our micrometeorite impact samples. We see only rare instances of the nanoparticles in our solar wind irradiated samples. Here are your fine scale parallel lines that are representative of the crystal structure within the sample. If we look at a higher resolution, you may be able to squint and turn your head to the left and see that there are some of these parallel lines that are embedded within that vesiculated region. These are nanoparticles that correspond predominantly to iron metal. So in our hydrogen irradiated samples, we see very limited evidence for these, and they do have a more metallic composition compared to our iron nickel sulfides we see in micrometeorite impacts. So once again, diverging results from our experimental samples. Okay, so why did we do all of this? We did this because we're leading towards the analysis of samples returned from the Hayabusa 2 mission. Those landed back on Earth in December of 2020. If you remember, that was in the peak of the pandemic, and Japan, they landed in the outback in Australia. Australia was very hesitant, as you know, to let anybody into the country. And so the Japanese government had to charter their own plane. The scientists that were on their part of the recovery team, I think had to quarantine in Australia for almost a month before they were allowed out of their hotel room to go and collect the sample. So it was quite the production to get the sample back, but was an incredibly successful mission that collected over 5 grams of material from 2 different sites on the surface. You can see when they opened up the sample containers, this is what the grains look like. We've got different grains of different sizes, up to a few millimeters in diameter. And so I was a co-I, a part of the Hayabusa 2 team, to look for signs of space weathering in these particles and analyze their microstructure and chemistry. And since the kind of mission has concluded, I've also proposed for some more samples to do analysis on space weathering from a greater sample set. So today I'm going to talk about results from 2 different particles. This one, A0058, you can see the scale bar there, a couple of millimeters in length. This was during the mission sample science phase, and then A0152 is something we've been working on recently in our lab at Purdue. Now, this isn't necessarily related to space weathering, but these videos are awesome, so I just wanted to show them. This is thanks to Scott Eckley at NASA Johnson Space Center. We wanted to do some X-ray computed tomography to try and understand what the internal composition of these grains look like. Now we're down at the scale of a couple millimeters here. So being able to see if there are diverse phases, if there are inclusions or clasts within the sample is important for knowing that we're sampling something representative of the material. So this is showing you kind of a 3D pass through of the grains. All of these bright spots that you can see popping out are sulfide particles. They are, things that have really high atomic number compared to this kind of darker gray ground mass that's surrounding it. That's the heterogeneous matrix material, phyllosilicates, carbonates, everything is much lighter. And Scott was awesome to kind of pull out this 3-dimensional rendering of one of our particles and show us the orientation and the distribution for some of these sulfide minerals in the interior structure of this sample. And so this is some data that we're hoping to work with in the future and correlate what we see in the internal part of the grain to the surface structure. That was just for fun. So now we'll get back to space weathering and talk about what kinds of characteristics we see on the surface of these samples. So on the left, I've got a secondary backscatter electron image from the scanning electron microscope. So again, you're looking at the surface in plan view. And what do we see? We see this melt texture that's distributed across the surface. It's highly vesiculated. It looks like there's bubbles and frothy. You also see some melt droplets or spherules that are spread out across the surface. And this is from one of our Hayabusa 2 samples. Just to remind you or compare that to our laser irradiated samples on the right, they look very, very similar. So the first time I collected these images, I was like, yes, I did not waste the last couple of years of my life doing these experiments. So we know on the surface, we've got microstructures that are consistent with simulated micrometeorite impacts on the surface of Ryugu. So what does that look like in cross-section in the transmission electron microscope? So now the surface of the sample is here. It was embedded in epoxy, so all the stuff's epoxy, and don't worry about that. And you're going into the grain interior in this direction. And this is one of our Ryugu particles. This is a Z contrast image, so higher atomic number appears brighter. And what you may notice is that, again, there's a melt spread out across the surface of the sample. There are droplet-like textures on the surface. There's also some that have more of a flat morphology. And there, if we take a higher magnification or closer look at this, these dark areas are vesicles or bubbles that are spread throughout the melt. They're also concentrated at the interface between the melt and the underlying heterogeneous matrix material. And each of these bright spots in here is a nanoparticle that is present throughout the melt deposit. Just to compare again from our TEM images of our micrometeorite impacts compared to the samples from Ryugu, we've done a really good job replicating these processes in the lab and being able to say definitively these are produced through space weathering on the surface of Ryugu. We can take a closer look at the microstructure and composition of these Ryugu samples, and in particular the melt deposit. The nanoparticles we can analyze using energy dispersive X-ray spectroscopy, which is our chemical mapping. There are hotspots in iron and sulfur for each of these bright nanoparticle phases. But one thing that was interesting was the distribution of nickel. It's very heterogeneous or patchy throughout the nanoparticles themselves, whereas the iron and sulfur is pretty uniform. There are regions of within individual nanoparticles that have nickel and regions that don't. We went in to look at the microstructure of these individual nanoparticles, and looking at these atomic planes, you can actually measure the spacing between those planes and match that to a particular mineral phase. So we were able to do that and show that within 5 to 10 nanometers of each other in the particles themselves, we have 2 different mineral phases. We have pentlandite, which is a nickel-bearing sulfide, and we have pyrrhotite, which does not have much nickel in it. So this was something very different from what we see in our experimental samples. Yeah, there were iron nickel sulfides that we produced, but they were monomineralic. They did not have this heterogeneous distribution of nickel. So it was something totally new from our analyses of the Ryugu samples. We can compare that to data from another particle that we've been analyzing after the mission sample science phase ended. This is work that's really being led by one of my graduate students, Lizette Melendez. She just presented it at LPSC. And again, we see in the secondary electron image, you're looking at the surface of the sample. There are deposits on the surface that are in relief from the surrounding material. But instead of being frothy and bubbly, this looks much more smooth in texture. So we wanted to take a cross-section of the sample to see how the microstructure compared to what we've seen in other Ryugu grains. So now we're in the TEM and you're looking at the surface and going into the grain interior in this direction. There are vesicles. They don't seem to be as intersecting with the surface of the melt or necessarily concentrated at the boundary with the underlying material. We also see these dark spots, which are the nanoparticles distributed throughout the melt as well. There are almost different generations of those nanoparticles. There's some very, very fine scale ones at the top and then larger ones at the base of this melt. Using our EDS mapping, we can look at the composition, again, dominated by iron nickel sulfides. But one thing that's interesting is that we can look then at the composition of the underlying material. And for this grain, we've got a dolomite grain, a calcium magnesium-rich carbonate grain that's the substrate for this melt deposit to be splashed onto. But this melt layer, similar to what we've seen in our other particles, is microns and microns in thickness. So it could be masking our detection or our understanding of what minerals are present underneath the surface of these space-weathered layers. And this becomes very important for one reason, and that is trying to interpret the spectral data from asteroid Ryugu. So in advance of sample return, the observations for the spectral properties of asteroid Ryugu, the spectrum is shown here in black for Ryugu. They wanted to compare it to different carbonaceous chondrites to try and understand, well, are we going to get a CI-like material or CM material or what? And blowing up this area around the 3 micron band, which is associated with water, the best matches for the Ryugu spectrum came not just from carbonaceous chondrites, but in particular, Avuna, which is a carbonaceous chondrite, but this sample had been heated up to 500 degrees Celsius, meaning it had been cooked. It had been, a lot of the water in those phyllosilicate phases is probably gone from their structure. It was dehydrated. So that led to the expectation that the samples coming back from Ryugu would be dehydrated. They would be pretty dry. That's not the case at all. We see tons of hydrated phases within our samples from Ryugu. So a new idea is emerging based on these observations for space weathering characteristics, which is that we are creating this chemically distinct, optically thick layer on the surfaces of the grains that is being produced by micrometeorite impacts and depositing melt onto those grain surfaces. And if you remember from our experiments looking at changes in the water band at 1.94 microns, we saw an attenuation of that water feature with both our hydrogen and helium irradiation, but with our micrometeorite impacts as well. So we have evidence from the laboratory that we can reduce that water feature, and now we're seeing it at the nanoscale in the Ryugu samples. Basically, we might be cloaking the surface of Ryugu and artificially making it seem like it's dehydrated when it's not. So what are the larger scale implications for this? Well, we know that we have micrometeorite impacts on the surface of Ryugu, and our laboratory experiments are really accurately replicating these characteristics with analog materials. One thing that's been interesting to compare to our other asteroid sample return mission, the Hayabusa 1 mission to Itokawa, is that we're seeing a lot more evidence for micrometeorites on Ryugu compared to Itokawa. Whether that's a result of having more sample, maybe we just didn't get the right grains, there were only about 1,000 particles from asteroid Itokawa, that's quite possible, or this could be a systematic difference that's affecting the surface of Ryugu versus Itokawa. But large scale, there's tons of C-type asteroids in the asteroid belt that do not show significant evidence for a 3 micron band. That has led to the interpretation that, we have different levels of hydration in these bodies in the main belt. But what if instead there's just a spectrum of potential space weathering, where more space weathered material that has had more time to develop characteristics of micrometeorite impacts, there are evidence for that hydration is being blocked or cloaked by this space weathered layer that's being deposited onto the surfaces of these grains. So this is all information from one particular asteroid. Wouldn't it be great if we could get samples from another carbonaceous asteroid? Well, what do you know? We are going to have samples back from asteroid Bennu returned by the OSIRIS-REx mission in September of this year. So we'll be able to do analysis on these samples and compare our results from Ryugu to Bennu. What's going to be very exciting about the samples from OSIRIS-REx are that not only is there a bulk sample that was collected in the sample canister, but they also had these stainless steel Velcro pads that are called contact pads. Each one of these circles that are spread across the head of the sampling mechanism that were the first things to come in contact with the surface of asteroid Bennu. We think that they have trapped the uppermost fine-grained layer of material on the surface of Bennu that has experienced space weathering. So I'm part of the team to look at these samples when they are brought back in September, and it'll be fascinating to compare those results to our Ryugu samples, in particular because Bennu shows widespread evidence for hydration. This has led to the interpretation that maybe Bennu and Ryugu are just different types of carbonaceous material, but could it in fact be that these asteroids are just experiencing or demonstrating that they have variable differences in terms of their degree of space weathering? We'll be able to hopefully tell that when samples come back from OSIRIS-REx in September. So stay tuned for our next data set from asteroidal return samples. So just to kind of finish up here, we are really expanding our understanding of space weathering across the solar system. We started in a framework of an Apollo, and I think a lot of people thought we had space weathering figured out. We knew it was happening to the spectroscopy. We knew it was happening at the nanoscale. And then samples from Hayabusa started to give us a couple of questions, but same types of minerals. There wasn't too many surprises. But samples from Hayabusa 2 and our understanding of carbonaceous asteroids have really revolutionized how we view space weathering as it operates across the solar system. And OSIRIS-REx is sure to do the same. And this process is really critical for future exploration targets. We're working on projects to understand space weathering on Mercury, which is going to be relevant to observations from Bepi-Colombo, the Psyche mission, how do metal-rich asteroids experience space weathering. Eventually, we'll have samples back from Phobos through MMX, and that's a unique environment where we have planetary ions as well as solar wind ions. And then finally, what about short-scale space weathering on the surfaces of comets? So if CSER, the Comet Nucleus Sample Return Mission, goes ahead, I'll be sure to look for evidence for alteration on cometary materials as well. So with that, I just want to say thanks in particular to the Hayabusa 2 team, a lot of my collaborators that are at JSC and have helped out with some amazing data, and then particularly my students and my postdocs who have been so instrumental in helping me explore space weathering across the solar system. So with that, I'm happy to take any questions.
All right, thanks so much, Michelle. That was fascinating. You see, we've already got some virtual applause in the participants section. So if you all have questions for our speaker, you can either type those in the chat box and I'll read them for you if you're shy, or you can just virtually raise your hand and I will call on you to unmute yourself. So we welcome questions now from the audience. And while people are working up the courage to ask their questions, I'll use my privilege as host here to ask the first one. So I may have just missed this in the talk. So for the Ryugu samples that you looked at, were you able to look at materials both from the pre-impacted and the post-impacted sites and see difference in the space weathering there?
Yeah, so great question. We do have samples from both of the sites, but right now we've only looked at site A, which is the pre-impact. But my student Lizette is, I think, maybe literally as we speak, transferring some particles from the C chamber, which is post-impact. So we'll be able to hopefully see if there's a difference from the material collected in both of those. That's part of our plan, yeah.
Awesome, that's exciting. Thank you. Okay, our next question is from Romy Hanna. Go ahead and unmute yourself and you can ask your question.
Hi, Michelle. Great talk, as always. I have two questions. The first one was for the Ryugu sample, you talked about micrometeorite bombardment, but did you guys see any evidence for solar wind implantation?
Yeah, great question. So in the particles that we've looked at, nothing that we can unambiguously say is solar wind irradiation. But one thing that we've been discussing kind of as a team more so is that these melt layers, these capping layers, they're really refractory, they're really robust, they're really hard, and they're probably less prone to any sort of damage, like through sample transport as it was landing back on Earth, as they're shipping the samples to us, and they're very robust. Whereas these, if we were to try and see something really vesiculated, which other people have seen, I would say They're less obvious than our micrometeorite impacts. They might be more prone to being destroyed just by kind of sample transport. So that's one thing that OSIRIS-REx is going to be really great for, because the contact pads, those grains should have stayed embedded in the pads the entire transit back to Earth, less bumping around, and so hopefully we'll have more evidence for preservation of just solar wind in those samples. What we're doing is we know that these surfaces that have melt deposits on them were likely at surface. Those grains were at the surface of Ryugu. So we're taking adjacent sections to look at in the TEM that don't have melt on them to see if they have evidence for solar wind irradiation.
Okay, thank you. And then the second question is, assuming that both asteroids were relatively hydrated in the same way. I mean, most people kind of argue that Bennu is more of a CM type or ungrouped C2 versus Ryugu, which is like more of a CI. But the water content between the two is not like crazy different. Have there been any thoughts floating around about why Ryugu seems much more space weather dehydrated than Bennu? Is there a surface exposure, formation, orbital reason?
Yeah, one thing we've been talking about is kind of the scale in terms of timing. So one thing I didn't talk about today is that there's also potential for generating water on the surfaces of airless bodies through solar wind irradiation, hydrogen combined with oxygen. But these processes have different timescales, right? Solar wind irradiation is consistent. It's happening all the time. And so early space weathering is going to be dominated by solar wind ions because they're grains that just hit the surface of Ryugu are going to be experiencing solar wind. Micrometeorites are more stochastic. It takes longer for the first effects of them to kind of build up. But then you're getting solar wind irradiation on top of the melt deposits, and the cycle, it's kind of a cyclical thing. So one thing maybe, that there's differences in terms of the surface ages for Ryugu versus Bennu, or maybe we're just hitting it at a cycle in its space weathering, time scale, that we're seeing more evidence for masking of hydration versus evidence for hydration. So we'll see. I'm not sure about, dynamics. Maybe that could be a possible question about, how long they've spent the last time they broke up, all those kinds of things. But yeah, I'll be curious to compare the samples for sure.
Okay, cool. Thank you.
All right, our next question we have coming from our chat box from Mike Ames. He's asking, are you planning to calculate the rate of mass loss of each studied object, more or less a rate of decay?
Yeah, we don't have plans to do that right now. But one thing we want to do is, I mentioned just at the top that you can look for these solar flare tracks, and then the concentration or the density of the solar flare tracks gives you an exposure time scale in terms of years. This is how many years the grain sat at the surface within like the top millimeters. And so we can compare, if we can get those solar flare track ages to the kind of characteristics that we see, we might be able to put more firm timelines on some of these processes. But a lot of this material is phyllosilicates, which don't preserve these solar flare tracks. We need kind of larger anhydrous silicate grains in order to be able to do that. But timescales and how long these things are taking is something we definitely want to explore.
Great, thanks. Okay, we have another question from Brian Balta. Go ahead and unmute yourself, Ryan.
Hi, Michelle. First, thank you for the excellent talk. So I found the TEM image showing the glass on top of a carbonate mineral to be really interesting because you had a big silica peak across there. So I've kept an eye on this on the lunar rocks for a while. Have you seen any relationship between the type of material you're finding at certain spots and the substrate that's actually being hit? And feel free to note either Ryugu or the experiments on that either way.
Yeah, so that we've only pulled a couple of sections, and that's the first one where we had such a significant difference in the composition of the melt compared to the underlying material. So I don't say we have enough statistical, observations to make that determination. But most of the melts seem like they have, that we've analyzed so far, seem like they have a roughly olivine-ish kind of composition, not stoichiometric, but kind of close to that, compared to the totally diverse types of materials that we're looking at are in the matrix. Our goal is to go in and also look at some iron or some sulfide minerals if we can, some magnetite for sure, to get a real diversity of phases that have melt on top of them and see if there is some kind of correlation. But I'd say too soon to be able to tell that. We're going to have to do a lot more analyses. Too bad for my grad student, but
Thank you.
yeah.
All right, we have another couple of minutes for anyone to ask questions. And if I wait a few seconds, I don't see them, I'm going to ask another one. So here's another comment from Mike Ames. Oh, but it's directed to me. So I'll read it to you. It seems we would make a great advances in materials degradation from space exposure by capturing the oldest man-made object in space and studying it, Explorer 1. I'm not sure that.
Yeah, I mean, it's interesting. I know there's some recent work that's been going on to kind of do these types of experiments on the Genesis panels that were out and, purposely exposed to the solar wind, but for a short duration, to see, just how quickly do these sorts of microstructural characteristics build up? Can we recognize them on those short time scales, or does it take, on the order of hundreds to thousands of years? So looking at man-made things that we send out into space is also an interesting way to kind of constrain this process for sure.
Thanks. And it looks like we got one from Paul Abel. Go ahead, Paul.
Hey, Michelle.
Hey.
Good to see you again. Go Canada. Gotta
Go
love it.
Canada.
So a question for you is, obviously, Itokawa, Ryugu, and Bennu, all different types of objects. Ryugu and Bennu, of course, are a lot more similar, even though they're very different. Bennu is much more heterogeneous than Ryugu, right?
Yeah.
So I was wondering, given that there's opportunity potentially for lots of sample at OSIRIS-REx, a lot more sample than Hayabusa 2 collected, are there any plans to look at any of the different types of class to see if there's any different rates of space weathering or different effects of space weathering on the different types of particles that may be collected, and just trying to get some hints on how surface types affect the space weathering, or effects, just seeing that and how that can be correlated on the same object, because you'll have the same exposure history, hopefully, in some cases,
Yeah.
depending when they're formed. So just some thoughts on that. It's something that's always sort of intrigued me.
Yeah, no, that's a great question. So, a lot of our emphasis is on the contact pads, but one of the things we're building into how are we selecting the grains we're going to look at out of the contact pads is, do we see diversity just, with our optical images in terms of color, in terms of texture, so that we might have the opportunity to see how the space weathering characteristics differ based on the underlying composition. But we're also going to look at samples, probably the finds from, at least the finds from the bulk sample as well, because we'll have a sampling of everything there for sure, and look for space weathering characteristics in the finds. And then the bulk, grain, stones, chips, whatever you want to call them in the sample, our plan is to try and evaluate whether of any of those rock chips have evidence for space weathering on them. Things like patinas, things like microcraters that you can just see on the surface of the stone. And that's important because we don't want to, just people want to do bulk isotopes and bulk elements and all kinds of stuff. But if there are special samples that might have a diverse composition, we want to scan them for space weathering first too. So I think we'll absolutely be able to get samples from, different lithologies, we'll call them, if they are there, and kind of compare them for sure.
Yeah, thanks. And a second question related to the water content. Again, bit of a surprise. Ryugu not really well heated at all. Has substantial water, like 6 to 7, 8% maybe by weight. the spectra from Bennu seems to suggest that it would be more hydrated than that. I wondered if you could comment on go on a limb and what you're expecting in terms of the water content. I know that's not your area of expertise, but it lends to the the volatile nature of the composition and how that may be different between the two bodies.
Yeah, I mean, as far as I'm willing to go is I wouldn't be surprised if it was more hydrated, but I don't want to put any sort of number on it. One thing we have been considering is this question of time scale and whether we're just going to see more evidence for solar wind irradiation versus these micrometeorite impacts and stuff, but I'm not going to put a number on it. I don't want Dante coming after me.
Okay, I won't call you a coward. No, thank you. I appreciate it. It's a great talk. Thanks a lot. Appreciate it.
All right, well, thank you. And I see that we're coming up to the end of the hour now. So I think I'd just like to thank you on behalf of all of us again. And if people want to express their appreciation in the chats and in the virtual applause again, there we go. Well, thank you for that fascinating talk and really a stimulating discussion as well, Michelle. You're welcome to come share more as we get some more data coming in.
Great, thanks so much. And thanks for the invitation and hope to see you all around Houston sometime soon.
Definitely. All right. Thanks for coming, everybody. And we will see you all in the next seminar. Have a great week. And thanks again, Michelle.
Thanks.